Limit involving prime counting function pi of n. So before we move to this limit, first of all let us have a general idea of pi of n. So the function pi of n basically finds the number of prime numbers, finds how many prime numbers are there which are less than n. So basically a number of prime numbers which are less than n. So let's say if you want to find pi of 10, then actually there are 2, 3, 5, 7. Okay, so there are 4 prime numbers. So pi of 10 is 4, and similarly pi of 20. Okay, 2, 3, 5, 7, 11, 13, 17, 19. Okay, so there are 8 prime numbers. So pi of 20 is 8. So similarly, now you can find out, and from Riemann and one other mathematician. Okay, so we do have a formula for pi of n, and that formula is that's not exactly equals to, but approximately equals to n by ln n. And the error bound for this formula goes to very very small and almost to 0 when n goes to infinity. And if you want to check this, we can just check for few values. Let's say pi of 10 will be approximately equals to 10 by ln 10. And that will be 10 by ln 10. That will be, let me use my calculator, 10 by ln 10, 4.34. That's approximately a round off, then 4. 4.34 will round off to 4. So this one is actually equal. Error is just 0. Now for pi of 20, or let's try to find pi of 100. Pi of 100 is actually 25. Now if we use the formula, okay, first of all pi of 20, that will be 20 by ln 20. 20 by ln 20, 20 by ln 20. That's 7. 6.67, which is 7. It's approximately 7. And the error is just 1, but the error percentage is going down. Of course it will go down because numbers are greater, so the error percentage will be going down. And pi of 100, it's actually 25, and if you use the formula, that approximation formula, we will get 22. That's nearly equal. Not equal, the 22. So the error percentage will go to 0 at infinity. So that's why we can use this formula, that pi of n is equals to n by ln n when n goes to infinity. Limit n goes to infinity. Okay, now so with this we are going to solve this problem. Okay, now this problem, first of all we will replace pi of n by ln n, because we said that its n is going to infinity. And for this one, this is n to the power 1 by n, so we can change that to e to the power ln of n to the power 1 by n, because e and ln just cancel each other out. And now this will be using the property of logarithms. That can be written as e to the power ln n, and then 1 by n comes in front, so by n minus 1. Now at infinity, ln n by n will go to 0. You need to know that fact, because n, it grows a lot faster than logarithm function. At infinity ln n by n will go to 0 because n grows faster than ln n. Logarithm grows slower than normal polynomial functions. So that's why. And if you want the proof, you can use L'Hopital's rule. Yeah, if you use L'Hopital's rule, this will be limit n tends to infinity. Ln n will be 1 by n, and n derivative of n will be just 1. So this is again 0. So basically, this thing over here is going to 0 at infinity. Yeah. Now, if we have something like e to the power approaching to 0, like something value, let's say we have some value x over here, and this x value is approaching to 0. In that case, e to the power x minus 1 will be equals to x itself. And if you want the reason for this, we do have a limit property that explains this formula, that e to the power x tends to 0, e to the power x minus 1 by x, that is equals to 1. So from this limit property, we can take x to other side, and this also holds true. Yeah. So if we have some values in the exponent of e, that's going to 0, and minus 1 as well, this expression will always be equals to x itself. Yeah, and the proof is this property. Now we can use these properties, yeah, and solve this problem. So basically over here, first of all, let me use the lasso. And let me just increase the screen. Yeah. Okay, over here the power is going to 0, and here minus 1 is there as well. So we will have n by ln n, and we can write the x over here. X is this power, which is ln n by n. Okay, now you can see that this actually cancel each other out, and 1 will be there. So it's just limit n tends to infinity of 1, and that's 1. So we have solved this problem. This problem was not that hard. It was just some limit properties that are known, and the definition of pi of n, that it's prime counting function, and the prime count graph also goes something like this, and prime counting function goes something like this. And yeah, and the formula for this was n by ln n when n goes to infinity. So yeah, that is it. Thanks for watching.